Good evening, everyone. Hello. How goes it? Hello, Yeet. Hello, Water Dude. How is everybody? Everyone doing good? I have had a good day so far today. Sunday is kind of like, I mean, for obvious reasons other than, or for reasons other than the fact that I stream math on Sunday. Sunday has become kind of like my non-work math day. And so Sunday is also the day that I go and do like private tutoring and things. I've got a few students that I tutor for some extra money on the side. And I also went rock climbing today. And so today has just been, you know, tutoring, rock climbing, doing some shopping. It's been a good day so far. Have you guys had decent days? Got something in my throat apparently. Drink some water. I had a productive day. Let's go! That's awesome. Certified productive gamer moment. The collar cone, thank you for the follow. Welcome in. Did I say that right? Collar? Who knows? You might know. If you know, let me know. Then we'll both know. All right. Everybody, pay attention. Eyes up, Buttercup. We're going to review a little bit of what we talked about last week, in case you weren't here and you don't remember. We're not going to go all the way into it, but we're going to go a little bit into it. And so, as you might remember, or you might not, we've talked a little bit about this thing called the difference quotient. Not plus. And so the difference quotient. And so this is the difference quotient. And in principle, what it is actually pretty simple. Is the intro music loud? I have not played Project Silverfish. And so if we were to graph f of x, then basically the idea here is that, you know, x plus h is some x value. And so this is like some input value. And then the f of x plus h up here is what we get as the output. And so this is some output. And so for some input value that we put in, we get some output value out that we'll put on the x or on the y axis. And so here are two values on the x-axis, and then up here we have two values which will end up on the y-axis. And same thing here, x can be really any number, where we'll have some input x, and that'll get us some output f of x. And so really what we have here is like, we could really think of the x plus h as like just an x value by itself. And so this could be like, you know, we have f of x1. If it's easier for you to think about it this way, this could be like f of x1 minus f of x2 over x1 minus x2. And so really, all we're talking about here is that we've got some effectively like a change in our y value over a change in our x value. And so really, this is just slope. This is another way to talk about the equation for slope. And then you might be like, but why have you gone and ruined my boy slope? The forward difference, but there's also a backwards difference and a central difference. Interesting. Are they pretty close to being the same equations? Maybe just with the h kind of moved around. Turn this down. Gotcha. That makes sense. But yeah, this is basically just slope. And so the big idea here is if you pick a value of x and a value of h, then you find the slope between 2 points. But the reason why we made this x and x plus h is because we want to be kind of particular about how we find the slope. And so here, I'll go ahead and write that this is just m. It's the slope. And so, in practice, what we kind of can see happens here with this difference quotient is we can see here I've got a value of a and a value of h, and I'm using a here instead of x just because Desmos wouldn't like it if I tried to say x equals something. Or maybe it would. I don't know. I haven't tried. But for the purposes of graphing and using the point at the same time, I've used h, and you can see here we've got a couple points, a comma f of a, and a plus h comma f of a plus h. And so you can see those are these blue and orange points here. And so if I keep a the same and I just change h, then you can see that the orange point moves around. And so the idea is, what we're doing with this difference quotient is we're finding the slope between a point at some x value and then another point h away on the x-axis. And so if I make a if I make a 0 and then I make h 1, oops, not q, 1, then you can see that our first point, f of a comma f of a, is right here at 0. And then our second point is over here, x equals like 1 away. Or if I make this 2, then you can see it goes 2 away on the x-axis. And so what we're doing is we're finding the slope between a point that is at x and then a point that is h away. And so the reason why we would do it this way in particular is kind of combining this with the ideas of limits that we've learned so far. What we can do is we can essentially use the limits to figure out, well, okay, then what happens to this slope as h approaches 0. And so as the distance between our starting point and our second point that we're measuring the slope from approaches 0. So as they get closer and closer together, kind of like I'm showing here. And so you can see, as they do get closer and closer together, if we kind of zoom out and look at it at a distance, it looks very much like we now have a tangent line. And so like a line that goes just through a single point of this function. but it just looks like that. If we zoom in, you can see that it does in fact still go through 2 points of this function. So it's not truly a tangent line. And so then you might say, okay, well, great, why don't we just make h 0? Well, if we make h 0, because of the way that we've formulated the difference quotient to be f of x plus h minus f of x over x plus h minus x, what we end up with, if we simplify this a single step further, is, is that this is all over h. Which means that if h is equal to 0, this is undefined. And so we have a case here where for the difference quotient, h cannot be equal to 0. And that's exactly why we want to use the limit. I do like this song, but that's not what I'm trying to listen to. There we go. And so you can see here, when I put these points on top of each other, making h 0 over here, then the line disappears, because now the slope is undefined. And so that's precisely why we're going to use limits for this instead. And so we can find the slope of a tangent line using this difference quotient if we instead take the limit as h approaches 0 of f of x plus h minus f of x over h. And so by taking the limit as h approaches this value that it's undefined at, we can still figure out what the actual value of this slope of a tangent line is. And so this would be the slope of the tangent line. And in calculus, we give this a special name. This is the derivative. The derivative is very special and very important. And so the derivative is useful for a whole ton of reasons. Namely, if you have any function, then you kind of find the slope of it, then what you're doing is you're finding the rate of change. This is very in-depth. Were you a teacher? In a sense, I am still a teacher. This is just kind of what I want to do. One of the many things that I wanted to do in my free time. But hi there, Machame. And so we call this concept of finding the slope of a tangent line in calculus, this is finding the derivative. And typically there's a couple of different ways that we write this. And so one of the ways that we would write this is that if this is the derivative of f of x. Oh, I didn't select everything. Just lasso it. And so if this is the derivative of f of x, then sometimes we would call this f prime of x. Or there's another way to write this too that's sometimes more useful, where we say that it's df of x dx. And so with this, I want to point out that there's actually kind of like two parts to this. And so there's the d dx, and then there's the f of x. And so really it's this right here is the operator. And so this is the part of this that's saying, okay, we are taking the derivative. And here with the prime up here, this prime is also kind of like our operator. And so this is basically us saying, okay, if we have f with this little asterisk here, then we're taking the derivative. Or if we have the function f with this d dx out front, then we're taking the derivative. One of the reasons that this version is a little more useful is because it tells us which variable we're actually taking the derivative with respect to. Hi, fool. I'm going to take a drink of water. Yes. Thank you. And so, for reasons that we'll kind of get to probably in a couple more streams of this, it's important to know what variable you're actually taking the derivative with respect to, because you don't always necessarily just take, the derivative with respect to an input variable. Sometimes you want to find the derivative with respect to other variables, or you have a function where you have multiple different variables, and you need to keep track of derivatives of one versus derivatives of another variable. And so, throughout kind of these streams, you'll probably see me write f prime of x, or you'll see me write d dx of f of x, which can also sometimes be written like this, but they mean the same thing. And just know that in both instances, we're talking about the derivative. In general, though, if you see me write like f prime of x, it's kind of just for the case where it's like, okay, we're taking the derivative with respect to x. Or, in the case of taking the prime of some function, you're pretty much always just taking the derivative with respect to whatever the input variable is. But that out of the way, so last week we spent a bunch of time figuring out different limit definition derivatives of different functions and doing different questions, and we had a great time, and it was a blast. But basically, like taking the derivative of something using this limit definition that we have right here takes a long time. And so what we use to kind of help ourselves through calculus is a handful of different derivative rules, where if we're taking derivatives of specific types of functions or specific arrangements of functions, then we can apply a derivative rule to basically make it so that we don't have to go through all the nonsense of using the limit definition of the derivative or using whichever definition of the derivative we want to use. Molybdenum! What a good element. I love that one. I don't know what its atomic number is, but thank you for the follow. Welcome in. It's in the... Is molybdenum in the 5th row? About what would that be then? 40... I'm going to say 45. Periodic table. If I get this right, this is such like a useless flex. It was 42. It was 42. And it was in the 5th row. 45 was rhodium. So let's see here. And so usually though, whenever you're taking calculus, or at least this is how it was when I took calculus, there was kind of a lot of just like, all right, here's a rule, have fun, use it, memorize it. And, that was great for whatever, to get through the class with, all the other engineering students. But for me, personally, I always like understand things better and remember things better when I actually have the proof of them. And so we're just going to read through each of these rules that they cover in here. And we're going to read them, and we're going to look at their proof, and then we're going to go through their proof themselves. I hate it when schools tell us to do that sort of thing. Yeah, it's just, some people are just like, I don't care about the proof. I just give me like something that I can write on my flashcard. I'm going to have a calculator for the rest of my life, etc., etc. But I hate it. It's lame. And for me, like going through and working through the derivation, or rather kind of like the proof of these different rules, by like on their own, it's like, I always like, oh, okay, like now I know where that comes from, and now I can kind of like work up to like now it's like that idea has more neural connections in my brain, really. And it's kind of like, I think of it like trying to like cut a path through a field. It's like, are you gonna walk all the way around the perimeter of the field on the sidewalk, or if you could, would you like to make a new path that goes, in a more direct route, or a more scenic route, maybe. It's a kind of a metacognitive approach to thinking, sort of. But yeah, and it's like, like one thing that I always think of, like it wasn't until like after I took differential equations and was taking like some other class where we were doing like more differential equation things that like it actually occurred to me like why the integration constant or like the derivation constant that we usually use in differential equations is like C1 e to the k, or like lambda t. And it's like, oh, it's because if you have this polynomial that's like in terms of the like this what is it called, an ODE, like an ordinary differential equation, then it makes sense that as you move from one derivative up to another derivative, if you want them to be the same or at least similar, then you should use e to the power of something, because the derivative of e to the power of t is e to the power of t, and so on. Right, exactly. But it's just like, it just didn't occur to me like at that time in the class, and I was just given this like sheet and a half of like different differential equation structures that like you had to try and like memorize, and like method of undetermined coefficients. Like, oh my gosh, when you understand like the actual purpose of what they're trying to do, it's like I don't even have to like, it's not memorization anymore, it's just application of concepts. Drives me crazy. Anyways, so we have kind of a whatchamacallit, trivial case here, where it's kind of just like the constant rule. And so, I don't think we necessarily need to work through this one on our own, but if we take the derivative of a constant, then you can see here that if we're taking the derivative of a constant, then it doesn't matter where on that function we like are looking for our value. If you plug in f of x plus h, or if you just plug in x, or you plug in any value, you just get the constant. And so regardless of what you plug in for your function, you get a constant minus a constant on top of your h or delta x, whichever you prefer to use. And that's just going to be 0. And so the limit as delta x approaches 0 of 0 is just 0, because the limit of a constant as whatever variable approaches anything is just going to be that constant. And so, yeah, that's what we get. And so the limit of a constant, the derivative of a constant is 0. And you can you can interpret it graphically too very well. Because if we know that the derivative is the slope of the tangent line, and so the slope of the tangent line is the same thing as our derivative, then a constant is just going to be a flat horizontal line. And so that's kind of like what we can see here in this graph. This would be f of x equals some constant. And this graph right here has a slope of 0. And so the slope of any tangent line to this function is also going to be 0. And so the derivative of a constant is 0. Okay, the power rule. And so this is a very important one. This is probably the power, or the differential, or the derivative rule that you'll use most often. And so you can see here it says, before proving the next rule, it's important to review the procedure for expanding a binomial. And then they say the general binomial expansion for a positive integer n is this. And they kind of gloss over this a little bit, actually. So this uses the binomial expansion formula. And I think when I was kind of planning this earlier this week, I thought it would be fun to go through and kind of show not just the proof for the power rule in terms of the binomial expansion, but to show that the binomial expansion works as well. And so let's go ahead and do that here. And so the idea for the binomial expansion formula is for us to figure out if we have like x plus y to the power of n, then what is this equal to for any integer n, for some value of n. And so it's probably helpful to kind of review just some easy cases. And so if we have x plus y to the power of 2, then we know that's going to be x plus y times x plus y, which is going to be x squared plus 2xy plus y squared. And this should kind of be familiar from, foiling and stuff, or at least you can imagine that we're going to take this portion and distribute it to each of these. And so this would be like the same thing as x times x plus y times x plus y. And then you can distribute these x's and y's individually, and then that will get us back up over here after recombining these xy terms. Hi, Wesley. But there's another way that I kind of want to write this that I think kind of makes the direction of where we're going with the binomial expansion a little more clear. And so here, with kind of like our algorithm for foiling, where we do kind of the first, outer, inner, and last, then one way you can think about this is we're just kind of going through and we're kind of finding all of the different combinations of multiplying these different things together. And so like another way I could write this is like we have x times x plus x times y, and then we have y times x, and then plus y times y. And of course here it's fine to note that xy is the same thing as yx because multiplication is commutative. And so, we could flip these around, and then if we were to flip them around and then add them, then we still get our 2xy, and so that's great. And then we can kind of continue with this sort of idea here, where if we have x plus y to the power of 3, then this would be x times x times x plus x times y plus x times y times x plus y times x plus x times y plus y times x times y, and then plus y times y times y. I think I did that right. And so here we have our x squared y terms. Or did I miss one? How many terms do I have? 7? I think I'm supposed to have 8. What did I miss? Move the y through. Oh, I missed y times x. Or I think I missed another one too. Hold on. What is it? And so if I just start with this y and I'm moving the y through, then we get y times x, and then now I have 2 y's, and so I can start with x times y, and then y times x times y. Oh, and then I gotta bump this y over, and so that'd be y times x. And then so we have the one with 2 y's where the x is in each position. And then we have the one with 2 x's where the y is in each position. And so then we'll have the one with 3 y's. Okay, yes. And so then here are our x squared y terms. And then here are our y squared x terms. And then, of course, we've got our x cubed term and our y cubed term. And so that still gets us our x cubed plus, we'll have 3 x squared y, so this will be plus 3x squared y. And then plus 3xy squared. And then plus y cubed. And so what we end up seeing here is these coefficients here in front of these values. So this coefficient here and this coefficient here with the 3, and technically for the y squared and the x squared too. The coefficient in front of this, you could think of this as like, this is the number of combinations of x's and y's where we have 2 x's and 1 y. And then over here, we have the number of combinations, or I guess rather it's permutations, because order does matter. And then over here with the xy squared terms, it's the same thing. It's the number of permutations where, we have 1 x and 2 y's. And so we can actually write this binomial expansion in terms. And so here, I'm going to put a question mark here, and I'm going to write it again down here. And so one of the ways that we can describe this binomial expansion is actually in terms of that combination formula, where, we can have, like, say, if this was, x plus y to the power of 6, then this would be like if we had 6 factorial, or here, I'll write it like this first, where this would be like 6 choose 0 of x to the power of 6 times y to the power of 0. And then this next term would be like 6 choose 1 of x to the power of 5 times y to the power of 1, and then plus 6 choose 2 of x to the power of 4 times y to the power of 2, and so on until we get 6 choose 6 of x to the power of 0 times y to the power of 6. Because basically, once again, what we're saying is, okay, for this first term, like we had for the cube, then we know it's going to have only x's in it. And so these are the ways that we can arrange it if we have 3 x's and 0 y's. And so 3x, and so in this case, it's 6 x's and 0 y's. And so then we know we're going to have x to the power of 6 and y to the power of 0. And then using that formula for combination, or rather permutations of things, then we can start to expand that out, where this would be like 6 factorial over 0 factorial times 6 factorial times x to the power of 6, y to the power of 0, or plus 6 factorial over 1 factorial times 5 factorial, and then times x to the power of 5, y to the power of 1, and so on, until we would again get 6 factorial over 6 factorial times 0 factorial times x to the power of 0, y to the power of 6. And so if we were to kind of write this in general, and so if we were to write this in terms for x plus y to the power of n, well, then this is going to be, it's going to kind of follow this pattern of n factorial over 0 times n factorial, or I'll kind of write it like this, where it's n minus 0 factorial, and then times x to the power of n, y to the power of 0, and then this would be plus n factorial over 1 factorial times, now it's n minus 1 factorial, and then times x to the power of n minus 1 times y to the power of 1. And then I'll write one more term here. And so this is going to be n factorial over 2 factorial times n minus 2 factorial times x to the power of n minus 2 times y to the power of 2. I'm going to add a plus dot 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 here. And then eventually this is going to come all the way down to y to the power of n. And so what we can see here is that as like this number right here increases, so does this number and this number. And then this exponent of n here goes down by 1. Or rather, you could think it's like that this number right here increases as well. And so it's like these are all going up by 1 every step. And so we could also write this as a Riemann sum. And so this would be equal to the sum as, let's see, let's use k. So as k starts at 0 and goes to n of n factorial over k factorial times n minus k factorial times x to the power of n minus k times y to the power of k. And so this is it. This is our formula for the binomial expansion. And so I just kind of want to reiterate again here. So where this comes from, this right here is the formula for basically like the permutations of things. So if I have 6 things and I want to know how many ways there are to rearrange like 3 of them or something like that, then I would do 6 choose 3. And so it's like if I want to know how many different ways there are to reorder these x's in these formulas, or these y's in these formulas with a set number of x's or y's, then I can do that with these permutations. And so that's where this portion of this sum comes from. And then it's just the idea that, okay, well, if your permutation is basically saying, okay, I'm rearranging this many x's and with this many y's, then the exponents of your x's and y's should match that for each of the terms. And so we got that. Yay! We've got the binomial expansion. And so the okay. And so just, I guess if you're using sigma, it's just a summation. Would that be just the better way to say it? And then, okay. Well, I was taught that wrong then, maybe. And then A choose B is for combinations by definition. Okay, and it might be that I'm remembering this wrong. I think, because it's the way that I always try and remember it in my head is that with combinations, order doesn't matter. And so for the same set of values, if you're finding the permutations of one set and the combinations of another set, then there should be fewer combinations. Which means, because it's the two formulas, it's like there's this formula where it's n factorial over just n minus k factorial. And then there's another formula, which is the one that we have here, which is n factorial over k factorial times n minus k factorial. And for the same values of n and k, then it's clear that this one will be larger than this one. And so yeah, this is the combinations. And this one is the permutations. And where I said that the order matters is actually not true, because we're treating these all as the same thing, because xxy and xyx and yxx are still all going to be x squared y. Yeah, okay. Gotcha. . Never thought I'd see math on Twitch. Well, I never thought I'd see you in my Twitch chat, and so we're both equally excited. Welcome in. And you as well, Castle Bravo. And so, yeah, okay. Well, thank you for that, Castle. It's a good reminder. No, it's okay. I appreciate it. And, you know, frankly, like, math is just all about being pedantic, isn't it? And so I appreciate it. But yeah, so now we've got our binomial expansion formula. And the reason why we went through all of this in the first place is because we want to help ourselves kind of figure out a strategy or figure out some way that we can show in general what the derivative is of just like some function to the power, like x to the power of n. So if we have f of x is equal to x to the power of n, then the question is, what is f prime of x? So what is the derivative of this? Well, if we were to just plug this in here, then kind of to our difference quotient, this would be the limit as h goes to 0 of x plus h to the power of n minus x to the power of n all over h. And so, but we have like a problem here. Without there being some exponent here, we can't just FOIL this out and cancel out those leading x to the power of n terms and, you know, then divide an h from everything on top and everything on bottom. Or can we? Because now we've got this binomial expansion. And so we can, in terms of a sequence that goes from 0 up to n, we can figure out what this x plus h to the power of n would expand out to. And so let's go ahead and kind of fill this in here. And so this will be equals, and then this is the limit as h goes to 0. And then I'll write out some terms here of this x plus h to the power of n if we were to expand that using the binomial expansion. And so that would give us x to the power of n plus, it would be 1 factorial, or no, so then it would be like 6 factorial over 1 factorial times 5 factorial times x to the power of n minus 1 plus, or times h. And then we could figure out what each of these factorial, no, not 6. I was in the mindset of 6 again. And so then this would be n factorial over n minus 1 factorial, because I was doing that example with 6. And then if we keep going, this would be n factorial over 2 to the factorial times n minus 2 factorial to, times x to the power of n minus 2 times h to the power of 2. And then plus dot dot dot. And then eventually this will be like n factorial over, now I'll put the n minus 1 factorial here, times 1 factorial. And so this is kind of like we've gone through almost n steps and we just have 2 steps left. Then this would be x to the power of 1. And so I'll just write that as x times h to the power of n minus 1. And then our final term, and I could have wrote the n factorial over 0 factorial n factorial here, but that's just 1. And then we'll get the same thing on the end here, where it would be n factorial over n factorial times 0 factorial, and that'll just be 1 again. And so this will be 1 times x to the power of 0, which is 1, and then times h to the power of n. And so this is what we get for kind of expanding this out using the binomial expansion. And then we have this minus x to the power of n on the end. And then that's all over h. And so now the magic comes in where this x to the power of n and this x to the power of n cancel out. And now what we can see here is all of these terms on top do actually have an h in them. And so we've got an h here, an h here. Each one of these will have an h in them. Then we have an h to the power of n minus 1 and an h to the power of n. And so we can actually cancel this h from the bottom by kind of dividing it into all of these h's on top, and that'll reduce the power of all of them by 1. And so if we do that, what we'll be left with is we'll have the limit as h approaches 0 of n factorial over 1 factorial is just 1, and so this will be over n minus 1 factorial times x to the power of n minus 1. And then h divided by h is just 1, and so then we'll have this times 1 here that I'm just going to omit. Then we'll have our n factorial over 2 factorial times n minus 2 factorial times x to the power of n minus 2 times now h just to the power of 1. And then I'll add our ... here. Then n factorial over n minus 1 factorial times 1 factorial, which is just 1, times x to the power of h, or times x and times h to the power of n minus 2, and then this will just be plus h to the power of n minus 1 on the end. Whew. And so now, the great thing about this is if we take the limit of this as h approaches 0, well then all of these h's in these terms here are just going to go to 0. And so that means when we take the rest of those coefficients and the rest of those variable terms and multiply them by 0, they just all go away. And so this whole portion on the end here is gone. And so this all goes to 0. And so what we're left with, after taking that limit then, is just this n factorial over n minus 1 factorial times x to the power of n minus 1, and we can actually reduce n factorial over n minus 1 factorial, where if you think about it, this is just going to be like n factorial. I'll do an aside here. N factorial is just going to be n times n minus 1 times n minus 2 times ... all the way down to 2 times 1, etc. And then n minus 1 factorial is almost the same thing, where it's just n minus 1 times n minus 2. I guess I should put parentheses around these. Someone's gonna beat me over the head with a calculator that shows my order of operations are incorrect. Times ... times 2 times 1. I guess I don't have to put parentheses around these guys, but oh well, too late. And then we can see that these terms all cancel. And so actually n factorial over n minus 1 factorial is just n. And so then what we've got is that this is actually just n times x to the power of n minus 1. What that means is that if we have any function where we can write it as x to the power of n, I guess I shouldn't say any function. If we have a function, generally speaking, that's x to the power of n, then we can say that the derivative of this function is going to be n times x to the power of n minus 1. And so really quick, we can say stuff like, now, instead of having to do that whole kind of like limit definition that we did last time, where we did, for finding something like x to the power of 2. And so before, to do like x to the power of 2, you would have to plug this in and expand it out and cancel out these x's and then cancel the h from the top and then have h go to 0 so that any h terms go away, and then you're left with the 2x. Whereas now, if I ask you, okay, well, what's the derivative of x squared? Well, then you can very quickly say, the derivative of x squared, we're going to bring down that 2 and then subtract 1 from the exponent. And so this will be 2 times x to the power of 1. Or, if we have x to the power of 3, then same thing, f prime of x will be 3x to the power of 2. We bring down that exponent and subtract 1. And so there we go. This is often called the power rule. And so this is the power rule for derivatives. And so there you go. Another rule down. And then we can kind of continue from the power rule and say, and so they make a good note here, which we can make too, where if we have, like, if we start with x to the power of 3, for instance, and we take the derivative of it, and we get 3x to the power of 2, if I take the derivative of that again, which I can denote with like 2 prime, so f double prime of x, then this is just going to be 3 times 2 times x to the power of 1. And so that's going to be 6x. And if I take the derivative of that again, then this would be f triple prime of x would be equal to 6 times. So if this is x to the power of 1, and I bring down that 1 in front, and then we'd have x to the power of our previous exponent, minus 1, then this gets us 6 times 1 times x to the power of 0, which is just 1. And so this is 6 times 1, which is just 6. And then if you were to take the derivative of this again, then we would be taking the derivative of a constant, which gets us 0. Perhaps a slightly more interesting case is, what if we take the derivative of, say, like 1 over x? And so if we have f of x, does that work for x to the power of x? No, it doesn't. And the reason is because if you're at that point, your exponent's not constant. And so you would have to do something different. I think there's like a non-elementary function for that. It's like I think you could rewrite that problem in terms of like the W-Lambert function. Or I guess you could make it e to the power of x times the natural log of x. Then could you differentiate that? Yeah. Because then it would be e to the power of x times the natural log of x times the derivative of x times the natural log of x, which you could find. But we haven't talked about the chain rule or the product rule yet. And so we don't know how to take that derivative. But I would like to get back to it. And so hold on to that idea, because we can actually tackle that later. And so it's not actually as complicated as I thought it was. But yeah, so if we have something like f of x is equal to 1 over x, then we can rewrite this as x to the power of -1. And then we can apply our power rule. And so f prime of x, we bring down that negative, or we bring down that exponent, so -1, then times x to the power of our previous exponent, minus 1. And so this would be negative 1 times x to the power of negative 2, or negative 1 over x squared. And so this power rule works for negative exponents as well. But instead of making the exponent smaller, it makes the exponent larger. Does it work for non-integer powers? Yes. And so that's a great question. You do have to be a little bit careful when you specify non-integer powers. Actually, I don't know that you do. Yeah, I think it does just work. Because if we have something, say, like the square root of x, then this is just x to the power of 1/2, which then if we were to take the derivative of this, that would get us, we'd bring down that exponent and then subtract 1. And so then it would be x to the power of 1/2 minus 1, which is going to get us 1/2 times x to the power of negative 1/2, which is going to be 1 over 2 times the square root of x. And so that does work. Neat. And so there's your power rule. And so the next one I think they're probably going to cover is the product rule. Okay, no, they have the constant multiple rule. And so, whoa, dog time. Yeah, so here they just take this constant here and they just kind of like move it out straight away. That is technically a theorem that they showed back here in 1.2, or I guess in chapter 1. And so if we go to the limits, can we find theorem 1.2? And so there are some limit rules where you can say something like the limit of the sum of the functions is the same thing as the limit of the functions, or like the sum of the limit of the functions. Let's see here. Okay, yeah, so here we've got the properties of limits that I was just talking about. And so if we have a scalar multiple of the limit, then if the limit of f of x is L, and the limit of g of x is k, then the limit of b times f of x is just going to be b times L, or the limit of f of x plus or minus g of x is going to be L plus or minus k of x. And then this is an important one right here too, where the limit of f of x times g of x is just going to be L times k. And the limit of f of x over g of x is just going to be L over k. And so basically what this means is that you can like separate limits as well. And so rather than just kind of thinking about it this way they wrote it here, what we can also say is that if we have something like the limit as x approaches c of f of x plus g of x, then we can also write this as the limit as x approaches c of f of x plus the limit as x approaches c of g of x. Or with the product rule that they gave for limits, then we can say the limit as x approaches c of f of x times g of x is going to be the limit as x approaches c of f of x times the limit as x approaches c of g of x. And so these ideas of these limit properties are going to be very important for what we show next, and that's going to be the product rule for derivatives. And so the product rule concerns ourselves with what happens if we have two functions of x multiplied together. And so what if we said that, I'm going to write it like this. So what if h of x is equal to f of x times g of x? And so that would mean that the derivative of h of x is going to be the limit. No, I shouldn't use h here. Give me a letter. Give me a letter. Capital F. Z. We'll use Z. Sure. We'll use Z. And so we have z of x. So z prime of x is going to then be the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. And so this is just taking our function z and plugging it again into that difference quotient that we started with earlier. And so now the idea is we're going to do some algebra and rewrite things a little bit so that we can figure out kind of like what we've got here and use some limit properties to be able to write this in a way where we can kind of make sense of it. And so what I'm going to do first is I'm going to add some terms to the top algebraically. And so we have f of x plus h times g of x plus h. And then I'm going to write this as minus f of x times g of x plus h, and then plus f of x times g of x plus h. And then we'll have our minus f of x times g of x. And it's all over h. And so you can see here, all I've actually done is I've added these terms right here in the middle. And so I've subtracted f of x times g of x plus h, and I've also added f of x times gx plus h. G of x plus h. And so effectively, I've just added 0 to this numerator. And so algebraically, we're allowed to do what I just did. I haven't broken any like math rules or anything. Because f of x times g of x plus h subtracted from f of x times g of x plus h is just 0. And so we're good. And so then what I'm going to do now is I'm going to kind of like group these terms up in a different way. And so I'm going to write this as the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x plus h, and then all over h. And then this is going to be plus, and I'm going to separate this into two different limits here, right here along this plus sign. And so then I'm going to make this plus the limit as h approaches 0 of f of x times g of x plus h minus f of x times g of x all over h. So far, so good. And so I've used that first property of limits that we talked about here, and I've just broken this fraction up into two fractions, and now we're taking the limit of those two separate fractions. And so what I'm going to do here for this one is I'm going to factor out g of x plus h. And then for this one, I'm going to factor out f of x. And so then what we're going to get after that is we have the limit as h approaches 0 of g of x plus h times f of x plus h minus f of x all over h. And then this will be plus the limit as h approaches 0 of f of x times g of x plus h minus g of x all over h. And now something really cool is about to happen. And so we remember the other limit rule that we covered just a moment ago, where if we have the limit of two things multiplied together, it's the same thing as the limit of each of those things then multiplied together. And so then we have that this is going to be the limit as h approaches 0 of g of x plus h, and then it's going to be times the limit as h approaches 0 of f of x plus h minus f of x all over h, and then plus the limit as h approaches 0 of f of x, and then times the limit as h approaches 0 of g of x plus h minus g of x all over h. And what do we have here, ladies and gentlemen, furs and friends, gays and gamers? Right here, we see that these are the limit definition of the derivative that we started with in terms of the difference quotient. And so this right here is just f prime of x, and this over here is g prime of x. And then we have here just the limit as h approaches 0 of g of x plus h. That's just going to be g of x. And the limit as h approaches 0 of f of x is also just going to be f of x. And so then what we have, when everything is said and done, is that the derivative of f of x times g of x, so the derivative of this product of functions, I'm gonna write it in, I'm gonna write it these two flipped around. And so this is going to be f prime of x times g of x plus g prime of x times f of x. And so if you have two functions of x multiplied together, then what you end up with is this kind of rearrangement of the derivative of the first function times the second function plus the derivative of the second function times the first function. And so if we do an example, and so if we talk about something like, we actually figured out what the derivative of natural log is last time. And so we went through that whole proof of finding the derivative of natural log, and we found that the derivative of natural log just ends up being 1 over x. And so if we were to ask ourselves something like, what's the derivative of x times the natural log of x? Well then, this is the same idea of this being our f of x, and this being our g of x. And so this is our first function and our second function. And so then we'll have the derivative of our first function, in this case is just 1, times our second function. I'll keep these colors. Times our second function plus the derivative of our second function, which is 1 over x, times our first function. Whoa, Pen Center. Wee, Prime subscriptions are cool. Yay! Thank you for the Prime subscription, Pen. How are you doing? Are you having a good day? And so then if we simplify this, we get that this is the natural log of x plus x over x, which is just 1. So apparently the derivative of x times the natural log of x is the natural log of x plus 1. Pen, you're missing all the fun. We proved so we first reviewed the difference quotient. And wanted to hang out while I have to mark exploratory data analysis reports. Okay. You want to chill in a Discord? Yeah, so we proved the power rule for derivatives, but before proving the power rule, we proved the binomial expansion. Because you need that to do that power rule. Wow, meth. I mean math. Not again. Listen, as long as you don't do the blue math. Is that what it... I didn't watch Breaking Bad. Is blue meth supposed to be like better or worse than normal meth? And so we proved the power rule, and then after proving the power rule, we proved the product rule, and blue math is 99% pure math. Excellent. Well, then we got that blue math in this stream today. I don't know, maybe this isn't entirely pure. Maybe my math is a little bogan. I'm gonna be right back in 1 second, chat. I must take care of the aminals. Okay, I'm back. Walt's meth is blue because of where he sources ingredients, even though meth isn't actually blue on its own. Ever. A fun fact, when Breaking Bad exploded in popularity, drug makers actually started adding blue food dye to their meth. That's terrible. Well, at least it's not like red food dye, right? Apparently, red food dye makes you crazy. And so, you don't want the meth and the food dye making you crazy. That would just be terrible. Wait, what? I'm mostly joking. I don't actually know one way or the other. But apparently, some people are like allergic to red food dye or something. But apparently it like makes some people like, I don't know, wig out. I don't know if it's like actually like science or if it's pseudoscience and people are just like, I don't want food dye in my food. I only want to eat natural food, or if there's actually some truth to it. I'm not sure. It's probably ketchup's fault. Yeah, because that's got loads of red food coloring in it. Not just tomatoes. They probably do add red food coloring to ketchup. Okay. So you guessed it. We have the product rule. There's probably also, therefore, a quotient rule. So I did prepare my thoughts for the product rule ahead of time. I've not actually thought out how exactly I'm going to do the quotient rule. I imagine we can probably just do it a similar way. Or at least a sort of similar way. Let's see if we can piece through it. And so, right, I thought of doing it that way, Jeff, but to show what... Is that the power rule, though? Because if we have g of x to the power of -1, wouldn't that be the chain rule? Well, okay. Power, product, power, and chain. Yeah, but we haven't done the chain rule yet, and I felt weird doing the chain rule before the quotient rule. It makes more sense to do the quotient rule now. I feel like, in my head. Maybe, for some reason. So, now what we've got instead is we've got two functions that are divided by each other. So we've got f of x divided by g of x. And we want to figure out what is the derivative of this. And so if we have the derivative of these two functions, well, that's going to be the limit as h approaches 0 of f of x plus h over g of x plus h minus f of x over g of x all over h. And so same thing, doing our limit definition of the derivative, plugging our function into the difference quotient, and then seeing what can we make of it. And so I'm going to go ahead and pull this h out of the bottom as sort of like a coefficient. And then I'm going to look at getting a common denominator on the top here. And so this will be the limit as h approaches 0 of 1 over h times And then I'm going to get a common denominator here between the two of these. So I've got to multiply this guy by g of x and this guy by g of x plus h. And so that will be, here, I'll write it out. F of x plus h over g of x plus h times g of x over g of x. Once again, g of x divided by g of x is just 1. And so this is just 1. And so we're just multiplying by 1. And so once again, just reiterating the fact that there's not anything algebraically like wrong with what we're doing here. We can multiply the top and bottom both by g of x over g of x. And then this is going to be minus f of x over g of x times g of x plus h over g of x plus h. And so there we go. And so let's do some simplifying here and then see what we can make of this. And so this will be the limit as h approaches 0 of 1 over h times f of x plus h times g of x minus f of x times g of x plus h all over g of x times g of x plus h. This maybe feels like we're getting somewhere. Maybe? If I swap this g of x times g of x plus h with the h out here, and so we have the limit as h approaches 0 of 1 over g of x times g of x plus h, and then this will be all times f of x plus h times g of x minus f of x times g of x plus h all over now h. And so this is sort of looking like the limit definition of one of our derivatives here, or it at least is giving me similar feelings to kind of what we had up here when trying to prove the product rule. And so I wonder if there's something that we can plug in here where if we add it and subtract it to the top, we would be able to simplify this to kind of get another couple limit definitions of the derivative like we had earlier. And so, because if we have an x plus h and a g of x, and then over there we have an f of x times a g of x, then maybe if we add and subtract f of x times g of x to this numerator, we'll be able to do some simplification. Hi, Fem. Welcome in. Good evening to you, too. Let's get Pen Center in here. Hello? Hello, hello.
Hello. How are you, Talos?
I'm doing good. How are you? You holding up?
I'm doing pretty okay. I accidentally burnt some pita.
Oh no.
So I'm a little...
Well,
I know it's a little crispy for my liking.
Well, do you at least have more pita that you could attempt to not burn?
No, it was the only pita that I have.
There's no more pita.
There's no more.
What a tragedy.
It's a classic Canadian problem. How are you doing, by the way?
I'm doing good. I'm having a good day today.
That's great to hear.
Woke up kind of in the not long before the afternoon. And then I got up at like 10:40 today or something.
Oh.
But I do some. So usually my Sundays include like a little bit of private tutoring that I do on the side, just to kind of make some extra money. Got some high school students that I work with. And then I went rock climbing and had a great session of rock climbing today. Got to climb some big walls, did a couple V6s. Actually flashed a V6.
What's a V6 and what does flashing a V6 mean?
Yeah. So rock climbing, it's so much like terminology. Like rock climbers have their own language basically. But basically like for bouldering, which are like short walls, like 15 to 20-ish feet tall, which I guess isn't that short. But for the shorter walls, they have a grading scale that goes from like VB or like V0 up to V whatever. And so like VB and V0 is basically just a ladder. And then V1 and 2 are like amateur climbs. And then like 3 and 4, sometimes 5, are kind of like intermediate. And then usually everything beyond that's like pretty advanced or like powerful.
So you're basically saying that you're a very advanced brute.
Yes, that's right. I am very capable at touching the rocks. My kobold ancestors would be proud.
I mean, I'm also proud of you.
Yeah, thank you. Fem says, I went bouldering with a friend of mine one day years ago, and it scared the daylights out of me. I have a phobia of heights. I'm very thankful that heights is not something that I'm scared of. Even though I wouldn't say I'm scared of heights, though, there is definitely, like, a fear of falling. Where it's like, you know, even if I'm not worried about the fact that I'm this high up, I would still very much not like to fall. But I actually have, for the most part, gotten over that. And, you know, even falling now is like, whatever, I know how to land correctly. I guess as long as I don't get too complacent.
I also feel like, Fem, like, we would have caught you. Like, if you were gonna fall, we would have caught you. All
right. Good. You said ball pit?
Ball pit.
It's just like, we would have caught you. Ball pit. Just put a ball pit at the bottom.
Yeah, easy. The easiest solution is what we strive for around here.
Mm-hmm. But no, I love rock climbing. And so, private tutoring, rock climbing, running some errands, and now coming home and doing some math streaming. It's a good day. It's a good day.
Yeah, I mean, the fact that you're doing math and enjoying the outdoors kind of at the same time, that like, it kind of blows my mind a little bit.
Right. I mean, it's technically an indoor rock climbing gym. So it's not like I touched grass or anything, but like, it's sort of close. I touched fake rocks.
Close enough. Close enough.
Okay, continuing what we got going here. And so my idea was to add and subtract f of x times g of x to the numerator here to see if we can get a similar simplification that we did when we were doing the product rule proof from earlier. And so having gone through it in my mind, this is looking pretty good, but let's see. And so we'd have f of x times g of x. And so I'm going to write the subtraction first. And then we're going to have plus f of x times g of x. And then we'll have minus f of x times g of x plus h. And then that's going to be all over... Whoa! Jasper the Happy Fox. Raid of 2? Hi, Jasper. There it is. The Jasper raid. What were you up to? Phasmophobia? I like Phasmophobia. I've not actually played it in a long time. There's this meme I saw of Phasmophobia that's kind of like, dang, that's sort of true. Where it's like, the game does have a bit of a steep learning curve, but it's like either like everyone dies every time the ghost hunts, or you're either like doing that or like kick flipping a crucifix off the ghost's forehead, circling it around the kitchen table. And I'm like, true. True. Ate, can I help you? Do you not have food? Go away. Stop rubbing your head on my microphone. I need that to be where it is. Stop it. Go. Away with you. Can I get this dingus on the screen? Here is my microphone right here. This is the back of the microphone. And so you guys may now watch as she just rubs her head against the back of the microphone. Congratulations, Jasper. And so then we get the limit as h approaches 0 of 1 over g of x times g of x plus h, then times, and then I'm going to break this fraction up right here. And so then this will be times f of x plus h times g of x minus f of x times g of x all over h. And then this will be plus f of x times g of x minus f of x times g of x plus h. Can you see where this is going yet, chat? Can you see where it's going? I can see where this is going. And so then I'm going to go ahead and... So we know that the limit of the product of things is the same thing as the product of the limit of the things. And so I'm going to go ahead and kind of distribute this limit through. Technically, this is going to be the limit of this times the limit of everything here in the brackets, but then this is the sum of these things in the brackets, and so then we'll have the limit of, like, the limit of the sum of the things is the same thing as the sum of the limit of the things. But at any rate, what we'll end up with is the limit as h approaches 0 of 1 over g of x times g of x plus h. And then this will be times the limit as h approaches 0 of this guy here. And I'm going to go ahead and factor a g of x out of this.
Does Talos talk too much, and also do you like cheese balls?
Do I talk too much? I think I talk the right amount. Maybe sometimes too much. And so then this will be the limit as h approaches 0 of g of x times f of x plus h minus f of x over h. And then I'm going to factor an f of x out of this one over here.
You've uncovered my deep love for cheese-flavored spheres of doom. And as for Talos, well, let's just say they have a wonderful way of filling the void with their chatter. But hey, at least Seven's gargantuan jaws can silence anyone if we need some peace to scheme on our world domination. After I retrieve the darn piece of paper from the top of this ridiculously tall fridge. Anyway, stay cute, yep.
feel like
Hello?
Evil Talos has a... There it is. I was worried Evil Talos had taken control of the microphone.
No, I think it was Ate rubbing her head against the USB port on the back. Ate, you gotta get out of here. I love you, but you gotta stop this. Let me go try and figure out what Ate wants. Do you want to go outside or do you want food? What's up with you? Be right back. What is the meaning?
Hi, chat. How are you doing tonight? I was trying to figure out what Talos was proving. It kind of looks like he's proving the quotient rule for derivatives. Is it a quotient rule? Also, I'm eating my burnt pita right now, and it's not that great. Hi, Famished. Hello. Where did I come from? I've been here the whole time. It is? Okay, so it's the quotient rule for derivatives. Okay. Yeah, I just got here recently too. I was at bingo, and we have this rule at bingo where if you make a mistake, they force you to drink your drink, and I was drinking rosé, and I made 2 mistakes, and I've had a lot of rosé right now. But I was thinking, like, over on the left-hand side, there's like that limit as like, it's like 1 over gx plus h, g of x and gx plus h, right? And I was like, okay, like as h goes to 0, that looks like g squared. This kind of feels like it should be the quotient rule.
Hello, I'm back. I'm not sure if I've solved any of my cat problems, but I did everything I could.
Well, welcome back in either sense of things.
Okay, yes, we're trying to prove the quotient rule. That's what we're doing here. And so we did the product rule last, now we're trying to do the quotient rule, and I think we're almost there. Because if I take this portion right here, I'm going to write it with the g of x plus h and the g of x the other way around. And so this will be f of x times negative g of x plus h plus g of x. And then this is all over h. And then once again, applying that product rule for the property of limits as opposed to the property of derivatives, even though they are, I guess, related. On the inside of these brackets here, then what we get is, kind of working it out as I go a little bit. The limit as h approaches 0 of 1 over g of x times g of x plus h is just going to be 1 over g of x squared. And then this is going to be times the limit as h approaches 0 of g of x, which is just going to be g of x. And then times the limit as h approaches 0 of f of x plus h minus f of x all over h, and then plus, and then we have the limit as h approaches 0 of f of x is just f of x. And then this will be times, if I factor a negative out of this numerator here, and so if I make this negative out here, then this will be now minus f of x times the limit as h approaches 0 of g of x plus h minus g of x all over h. And look at what we've got here. Well, well, well. The limit as h approaches 0 of f of x plus h minus f of x all over h. That's just going to be the derivative of f. And the limit as h approaches 0 of g of x plus h minus g of x all over h. That's just going to be the derivative of g. And so if we combine everything that we've got here together, then we have that the quotient rule tells us that if we have f of x divided by g of x, and we're taking the derivative of that, go get in your spot, Ate. Is this intriguing to you, Ate? You want to get into the blanket? Go. You simply must go, Ate. You gotta do something. You cannot sit right here. I need this space.
Ate is very intrigued at the quotient rule.
Mm-hmm. Excuse me. Go. And so if we put this all together, now we have that this is 1 over g of x squared times all of this stuff. And this stuff is f prime of x times g of x minus g prime of x times f of x. And then this will be all over... I'm not pleased with that line. All over g of x squared. We did it! That's another derivative rule. And so it ends up being, I think, usually the way that it's like taught to students, or one way that it's taught to students, is it's like the top is very similar to the product rule, except instead of plus, it's minus. And so it's, instead of derivative of the first function times the second function, it's derivative of the top function times the bottom function minus derivative of the bottom function times the top function.
Did you ever have like any sayings or whatever that like teachers would like say to you?
Not for the quotient rule, I don't think so. All right, good night, Soffle. Thanks for stopping by.
Bye, Soffle. I was always told, like, have you ever watched The Magic School Bus, or am I totally dating myself, Talos?
I have, but it was like in elementary school.
Because I was always told, like, it's low, like, if G is the low function and F is the high function, I was always told it's low D high minus high D low all over low squared.
You know,
And
now
it always
that
reminded me of, like, yeah.
now that you mention that, that does sound familiar, but I don't think that mnemonic was ever like useful to me. VDU minus UDV all over V squared. I have like a UV minus VDU, or like technically it's integral of VDU thing that I have stuck in my head for remembering integration by parts. I just remember like my teacher like pointing at VDU and going like, it's voodoo! I feel like that's how a lot of people feel about integration by parts.
It is a little bit of voodoo, yeah. Can I add like a weird kind of like random small commentary?
Sure.
So you did this like really cool thing, if you go back a couple lines, where like you just added 0, right?
Yeah.
And for those of you kind of just learning calculus and starting to kind of see some of the algebra that kind of happens in the background, like this idea of adding 0 in order to create these like factor pairs or like create these pairs of things is like, it happens more often than you would think. It's like a very common strategy to help you break apart things. And I actually, like in my real analysis class, I think I had to use that like 2 or 3 different times this weekend.
Nice. Yeah, I mean, it makes sense. And that's what we did for the product rule as well. And so just kind of like...
Oh, nice.
And so we kind of did the product rule and the quotient rule sort of by the same strategy. either adding 0 creatively or multiplying by 1 creatively. Some of the oldest math tricks in the book. That's true. That's all algebra is, really, in a way. You're either saying both of these sides are equal, so you can apply the same operation to both sides because it will equal the same thing, or you're just adding 0 or multiplying 1 somewhere. Okay. Now, so we've got the product rule, we've got the quotient rule. Here, we should do an example of the quotient rule. Let's see, if we go down here, give me a question. Okay, use the quotient rule to find the derivative of the function. Let's do this first one, x over x squared plus 1. And so if we say, okay, f of x is equal to x over x squared plus 1, then we have a top function and a bottom function. And so the derivative of f of x is going to be the derivative of the top function, which is just 1, times the bottom function, minus the derivative of the bottom function, which, if you remember, by the power rule, we're just going to bring this exponent of the 2 down and then subtract 1 from it. And so that's going to be 2x, or 2x to the power of 1. And then the derivative of 1 is just 0. And so this is just going to be 2x, and then times the top, all over the bottom squared. And so if I do some simplifying here, maybe something nice will happen. We get f prime of x is equal to x squared plus 1 minus 2x squared, all over x squared plus 1. And so this is going to be negative x squared plus 1 over x squared plus 1 all squared. Got my squared here. OMG, brackets around x squared plus 1, my anxiety. I caught it. I put him in there. Or one of these must be 0 is the other big trick, although that's a classic to anyone doing quadratics. I think I understand the heart of your message, although I didn't parse it properly, I think. But yeah, classic algebra. Multiplying by conjugates, or whatever. Uh-oh, she's coming back. No. You're not allowed to rub on the microphone anymore, apparently. I don't make the rules. That's just how it is. Well, do you want to, like, go outside again or something? You were just outside. What do you want? Should I turn the cat cam back on? Is that what you want? This is literally my microphone, like right here. She's like under the microphone, which is on like a boom arm. D. Well, you don't like my D? My D command? It's so that I can fit it all in the title. Because people are like, how do I join the Discord? But they don't actually type exclamation point commands. But then also like, I only have 140 characters for my title, and that's not enough. Ate, please. See, look, Ate, now the webcam is frozen too. What are you gonna do? What are we even doing here? The webcam's not coming back on. You're breaking everything. Okay, give me 1 second, chat. I'll be right back.
Hello, chat. I'm back. I know, Color. Ate's so adorable.
Okay, I'm back. Ate is not actually here. The webcam is just frozen. I fix. I won't disturb though, back to lurking. You have my explicit permission to disturb, but you may also choose not to. Let's see. Where was I? Okay, yeah, so we've got this. I don't think there's any real simplifying to do here. I think it's just this. And so the derivative then of f of x is negative x squared plus 1 over x squared plus 1 all to the power of 2. Does that seem right? Seems right to me. Yeah. Okay. Let's do another. Let's do this one, number 10. X squared over 2 square roots of x plus 1. And so, f of x is equal to, what was it? X squared over 2 square roots of x plus 1. That sounds right. And so then f prime of x should be the derivative of the top function. And so this is going to be 2x by our power rule times the bottom function, 2 square roots of x plus 1, minus the derivative of the bottom function. OneNote looks good, but Zornal plus plus looks good too. I am admittedly looking for some other like good note options, mostly just because like, I don't know, I've seen like the kind of note taking apps that like Apple has, where it's like if you draw a line and then you hold it, it will automatically be like, ah, you're obviously trying to draw a line, and flatten it for you, and that just seems really nice. And so I need to look at other like note apps to use for this stream. I do like though with OneNote how you can kind of like change how everything looks. And so like I've got this like black layout, but you could, oh god, you could make it white if you wanted to. Or you can change the page color or add grids and stuff like that. But you can probably do that.
How dare you say that we shouldn't be using white OneNote? How dare you? I feel personally attacked.
I switched it for the sake of demonstration, and I still feel flashbanged. I don't know if my corneas will ever recover from this. So now for this question, for the next part, so it's going to be the derivative of the bottom, then times the top function. And so we got to figure out what the derivative of 2 square roots of x plus 1 is. And so so I'm just going to do that off to the side here. And so 2 square roots of x plus 1. We're taking the derivative of this. I'm going to rewrite this as 2 times x to the power of 1/2, and then plus 1. And then I'm just going to apply the power rule here. And so I'm going to bring this power down. So it's going to be 2 times 1/2 times x to the power of now negative 1/2, because we subtract 1 from that exponent. And then the derivative of 1 is just 0. And so this is our derivative here. So let's clean that up just a tiny bit. 2 times 1/2 is just 1. And then x to the power of negative 1/2 is going to be 1 over the square root of x. And so then back over here, the derivative of the bottom is 1 over the square root of x. And then this will be times our top, which is x squared. And then this is all over 2 times the square root of x plus 1. Pen, what's your take on rationalizing functions?
I don't even know really what that means, because is the result actually going to be a rational number?
Not necessarily, I think. But the way that I had always heard it is that, like, a long time ago, a bunch of math guys in a math room decided that we don't like it when there's radicals in denominators. And so we rationalize functions to basically make it so that there aren't any radicals in denominators. And so I guess in a way it turns what's definitely maybe not a rational number into a more rational number by the denominator having no radicals. But sometimes radicals are like integers, and so it could still be rational. I don't know.
It always feels a bit weird to me. Like it just feels like a weird term to use, I guess, right? Because all you're really doing is kind of moving the square root around, and it's not necessarily making it rational, if that makes sense.
I mean, I guess more like, was that not something that you were like taught to do in class?
Oh, totally. Like, I was definitely told that I should think about doing it.
Right.
And maybe I'm being a naughty college professor by like not forcing my students to do it, because I don't personally care that much. But
right. I mean, I feel like it's always seemed like the sort of thing where it's like you could do it, but if you don't, it doesn't really change anything. At least not like in a way that seems particularly meaningful. Right? Yeah. So this is what we're left with here. And I think I could definitely do some simplification here. Like, I could turn that... Actually, I will do this one. And so this x squared over the square root of x is the same thing as x times the square root of x. Because this will just be... so this is x to the power of 2 over x to the power of 1/2, which then we can use our exponent rules to make that x to the power of 2 minus 1/2, which will be x to the power of 3 over 2, which is x times the square root of x. And so then we have 4x square roots of x minus an x square root of x. And so this will be 3x square roots of x plus 2x all over this squared, which I think I will just leave it like this. But yeah, thus far, I do not know when rationalizing a function actually makes it so that you can do something that you couldn't do before. I mean, I guess sometimes it does just make it easier to do algebra. But yeah, point being, I don't think I'm going to rationalize this with this square root of x on the bottom. What would I have to do? I'd have to multiply this by, like the top and bottom, by 2 square roots of x minus 1 squared. And so 2 conjugates for the 2 radical factors on the bottom. Gross.
Yeah, it feels like super niche to me. Like every once in a while you'll have to do it with like a limit, or every once in a while you have to do it with a logarithm or something, but it seems very, very few and far between.
All right. So now, how am I going to prove the chain rule? So I've always seen the chain rule written like this, where you have dy dx, and so that would be the derivative of y with respect to the variable x. You can represent it as dy du times du dx, which would look like you have this du on top and bottom that would cancel each other out to get you dy dx, which is like a very nice idea, and visually it seems like it works that way. But I know that like in the background, mathematically, that's not actually what's happening, because we're saying that this is the derivative of y with respect to u, and so this is like an operator, like the du or d du of y times the d dx of u. And you can't, like, the d du and the u, like the d du in this left part here is an operator, whereas the the u over here is the variable. And so they can't cancel out like that. And there's several parts where like something like this sort of happens in calculus, where they kind of like make it look like these differential terms cancel out. But is there a better way we can show that? And so is there another way we can kind of reach the conclusion of the chain rule without just being like, look, it makes sense, doesn't it? When it actually doesn't. And so it looks like here they're using the alternative form of the chain rule, which is if you have the derivative of f of g of x. Oh, I guess I should back up a little bit and mention too that the chain rule is for functions that are like when you have functions nested inside of each other. And so like here, without the examples they give is like without the chain rule, we have a function that's just x squared plus 1. But in a place where you would use the chain rule, now it's the square root of x squared plus 1. The x squared plus 1 function is inside of the square root function. Or like here we have sine of x, but on this one we have sine of 6x. The linear 6x function is inside of the trigonometric sine function. And so one function inside of another. And so the chain rule tells us how do we go about differentiating functions that are nested inside each other, that are composed together. And so at the start of their proof down here, so let's just read through this. And so they say let h of x be f of g of x. So g is composed inside of f. Then, using the alternative form of the derivative, you need to show that for x equals c, that h prime of c is equal to f prime of g of c times g prime of c. So that's what the chain rule tells us. And so then what they say is an important consideration in this proof is that the behavior of g as x approaches c, a problem occurs when there are values of x other than c such that g of x is equal to g of c. So what this is saying is that this particular proof that they're about to show perhaps does not always work if there are multiple values of g of x that are equal to g of c. That's my takeaway. Appendix A shows how to use the differentiability of f and g to overcome this problem. For now, assume that g of x is not equal to g of c for values of x other than c. In the proofs of the product rule and the quotient rule, the same quantity was added and subtracted to obtain the desired form. This proof uses a similar technique, multiplying and dividing by the same non-zero quantity. Oh, okay. So I guess maybe if that's the case, then we can just give this a swing ourselves. And so I wasn't sure if it was going to be that simple. Sorry, just throwing my pen onto my floor. Not throwing pen, just my pen. Anyways, so if we have f of g of x, I'm not your pen. Well, I mean, we haven't established that necessarily. Do you want to? Never mind. So if we have f of g of x and we're going to take the derivative of this, then we're going to plug this into our difference quotient. So we have the limit as h approaches 0 of f of g of x plus h. Oh no, they're using the alternative form of the derivative. And so there is kind of like a slightly different form of the derivative where it's like instead of doing the difference quotient, there is another form of the derivative that we can use. Here, I'll write it in like a box over here on the side, where instead we can say that the derivative of h of x evaluated at a specific value c is equal to the limit as x approaches c of f of x minus f of, or not f, because I wrote h. Why did I write h? H of x minus h of c all over x minus c. Is that correct? Because that's basically just saying, yeah, we're letting the difference of y and the difference in x on the top and bottom both approach each other. Okay, that seems right to me. And so this would end up, so if we use this version of the derivative for this proof, then we'll go ahead and have x approach c of f of g of x minus f of g of c all over x minus c. And then okay, yeah, I kind of see where this is going, where if we can show, so if we can somehow get f of g of x minus sorry, I'm trying to think here. Okay, let me see. What did they do? And so we've got this. And so the idea here is that by oh, I see. Okay, so they multiply a top and bottom by g of x minus g of c, and then swap these denominators to make the inputs of f match the values that we have on bottom. And so after that swap, we have f of g of x minus f of g of c over g of x minus g of c. And you can imagine that kind of being like a substitute. Like basically it's the same sort of thing where it's like we could say now that like this is x, and so this would be like f of x, and this would just be x, and this would be like f of c, and this would be c. And that matches that current like initial definition of the derivative. Yeah, so this is another case of kind of multiplying by 1. So g of x minus g of c over g of x minus g of c is just the same thing as 1, because anything divided by itself is 1. And then after that swap, we get the same thing over here, where we just have g of x minus g of c over x minus c, which kind of matches that initial kind of secondary definition of the derivative. Now there is kind of the note here that after doing this just shows that, you know, that works when evaluating these derivatives like at a given point. But if you just kind of like, you can, other than this case here where they say that like you have to watch out for functions where there are other values of x such that g of x equals g of c, then you can kind of say, okay, well, for any functions that, like any function h that is f and g composed together in this way, then this statement is true as x approaches c. And so let's go ahead and work through that ourselves for posterity. And so if we multiply the top and bottom here by g of x minus g of c over g of x minus g of c. I squeeze this bracket in here. Then we get the limit as x approaches c of, well, these multiplied together, but I'll go ahead and make that denominator swap now. And so this will be f of g of x minus f of g of c all over g of x minus g of c. And then this is going to be times g of x minus g of c over x minus c. And so you can just see here that we have swapped these denominators. And so what you can see here, if you are astute, is that this g of x here, can I highlight it correctly? And so we have this g of x here and this g of x here, as well as this g of c here, and this g of c here. And so what we're saying, in other words, is that basically for this function of, like this function f here, we have this same input to f up here as we have as that value of g of x here on bottom. I don't know if that sentence actually like worked at all, but basically like this input of f is the same as this value right here on bottom that I've highlighted both in orange. And then same thing for g of c. So this input to f of g of c is also right here on bottom. And that essentially mirrors this alternative definition of the derivative that we have up over here, where we have h of x minus h of c over x minus c, except in this context, this x and c are just g of x and g of c instead. But what that ultimately means is that this portion right here, if we kind of distribute this limit through, essentially using that product rule property of limits, then the limit as x approaches c of all of this will be f prime of g of c. And then same thing over here. This one just more directly mirrors this definition of the derivative that we have here evaluated at a point. And so then this one will just be g prime of c. And so if we say that h of x is equal to f of g of x, then h prime of x is equal to all of this. And so h prime of c is equal to f prime of g of c times g prime of c. And then assuming other properties about f and g, then we can say that this is true for h prime of x as x approaches any value of c. But that's still assuming certain properties about the continuity and differentiability of f and g, presumably. Here, let me let the dogs in. Give me 1 second. I want to say, I bet that there's like a fun way that I could show the chain rule just using like anti-derivatives and things. But that is beyond where we are right now. I remember one point I went through and kind of like algebraically showed just for myself that like what is it? Like separation of variables works for like simple differential equations. Because that's kind of like another case where you sort of like fudge it and like separate like a differential term. Which isn't something that you can actually do, but it like works, quote unquote. And I was like, okay, well, if that's not actually what's happening, then what is actually happening? Who knows? Maybe from these side topics that we're having, what I'm learning is after teaching calculus, I need to teach differential equations. Okay, but there you go. We have ourselves a chain rule. Whoa, it all turned purple. I'll make it gold. Why does it look like that? Oh, it's probably because it's like it was a pencil instead of a marker. As this light blue is a pencil instead of a pen. Oh well. What else is there? And so that's kind of all of the sort of initial derivative rules that you really need. And so let's go to the end. And so I'm going to save implicit differentiation and related rates for next time. But let's go to the end of this chapter and take a look at some questions. And see if we can do some derivatives for the next 30 minutes or so. The limit on the left needs a lot of love. Okay, let's do some of these questions here. And so use the product rule or the quotient rule to find the derivative of the function. And then we'll also do some of these down here, 53 through 64. Let's see. Another thing that we didn't do so far yet, anyways, is the derivatives of the trig functions. And so last stream we showed the derivative of log. So we proved the derivative of natural log is 1 over x. with the limit definition. I did not prove the derivative of arctangent. But maybe we can prove the derivative of just some of our trig functions. And so let's see, how is this going to work? And so if we say f of x is equal to sine of x, then f prime of x, and so we don't have a rule for this. You know, it's like there's no way that the power rule, product rule, quotient rule, or chain rule necessarily helps us with just finding the derivative of sine of x, because sine is kind of like its own operator, its own function. And so let's go ahead and set this up with our difference quotient. And so this will be the limit as h approaches 0 of sine of x plus h minus sine of x. And so all over h. So my first thought is maybe with the sine of x plus h, maybe we can create some more terms here by breaking this up with the sum to product identity. Let's see, can I remember what that is without looking it up? This would be the limit as h approaches 0 of, let's see, I think for sine, they're both sine, cosine, and the signs in the middle don't match. And so maybe it's this sine x cosine h minus sine h cosine x minus sine x. Did I get it or am I wrong? I guess I'm not sure, so I'm going to have to look it up anyways. Let's see. Sum and difference identities. Ooh, I was close.
I've always learned that sine is same sign, right?
Apparently. That is correct. And so looking it up, yeah, the signs for sum and difference with sine, the signs in the middle match, and for cosine they don't.
Fun fact: if you want the mnemonic, sine of the sum should be the sum, and sine of the difference should be the difference.
But it makes sense. So if it's sine, then the signs are the same. That makes some sort of twisted image of sense to me. Okay, I'm kind of seeing maybe what is going to happen here, where if we have the limit as h approaches 0, and if I take these two terms that have a sine x in them and group them and factor that sine x out, then we'll have sine of x times cosine of h minus 1 over h, and then plus the limit as h approaches 0 of this middle portion here. And I'm going to kind of pull this cosine of x out. And so this is going to be the cosine of x times sine of h over h. And so this cosine of h minus 1 over h and sine of h over h, these are actually limits that we proved a while back when we were first talking about limits, specifically in reference to the squeeze theorem. And so if I graph sine of x over x, then you can see as sine of x over x approaches 0, it's technically undefined, but you can tell by looking at it that it approaches 1. Or was this in terms of the squeeze theorem? No, I don't remember. But same thing if we have cosine of x minus 1 all over x, then you can see as this approaches 0, it also approaches 0. And so for these limits here, this cosine of h minus 1 over h, this goes to 0 as h goes to 0, and this sine of h over h goes to 1 as h goes to 1. And so then what we get is sine times 0 plus cosine times 1, and so that just gets us cosine. And so then we get that the derivative of sine, and so sine of x prime, is equal to cosine of x. That was not as hard as I thought it was going to be. Let's see, let's do it for cosine now. And so then if we say instead that f of x is equal to cosine of x, and we want to find f prime of x, that's going to be cosine of x plus h minus cosine of x all over h. I forgot my limit. A calculus professor somewhere is going to take off all points for this question. And so then we have the limit as h approaches 0 of this. And so then we're going to do the same thing where we're going to expand this out with the sum and difference identity for cosine. Now, does it go sines first or cosines first? I'm gonna take my 50-50, and I'm gonna say it's cosines first. And so this is gonna be cosine of x times cosine of h minus cosine, or now it's sines. So now it's minus sine of x times sine of h. Is that right? Is that right? Is that right? Is that right? It is. Dang, I'm so good at math. And then minus cosine of x all over my beautiful line and h. And so then we're going to do something very similar to what we did last time, where I am looking at this limit that we have here, and I am seeing that here we have a sine of h over h that we can take advantage of. And then if we have this cosine of x that we factor out of these two terms here and kind of group them together, then we'll be left with a cosine of h minus 1 over h if we factor that cosine of x out. And so let's go ahead and do that. And so then we'll have cosine of x times cosine of h minus 1 all over h. And then I'll go ahead and pull this negative out. And so then this will be minus the limit as h approaches 0 of sine of x times sine of h over h. And then same thing, we talked about these limits like literally 3 minutes ago. Come on, why can't you remember these? And so as sine of x over x approaches 0, we get 1. And as cosine of x minus 1 over x approaches 0, we get 0. And so this goes to 0, and this goes to 1. And so we are left with negative sine of x. And so cosine of x prime is equal to negative sine of x. And so now we know that the derivative of sine is cosine, and the derivative of cosine is negative sine. And so, fantastic. Now we have what we would need to show what all of the other trig identities are as well, or what all the other derivatives of the trig functions are. And so we could do like the derivative now of tangent. And because the derivative of tangent is going to be the same thing as the derivative of sine of x over cosine of x. And we have now, thankfully, covered the quotient rule. And so this will be the derivative of the top times the bottom. And so the derivative of the top here is going to be cosine. And then times the bottom is cosine again, so that's cosine squared of x. And then minus the derivative of the bottom times the top. And so the derivative of cosine is negative sine of x, so this is going to be plus sine of x, and then times the top, which is sine of x again, and so this is sine squared x, all over the bottom squared, and so that's going to be cosine squared of x. Well, cosine squared x plus sine squared x, that's just 1. And so this is 1 over cosine squared x, which gives us secant x, or secant squared x. I have a very needy puppy that might just walk now. Okay, well, thank you for hanging out, Pen. See you later. Say hi to Reese for me. And so then the derivative of tangent is secant squared x. Sweet. And we could go through similar processes of saying, okay, well, what's the derivative of secant? And what's the derivative of cosecant? And what's the derivative of cotangent? But let's just do those as we go, as we need them. And so bearing in mind that now we know that the derivative of sine is cosine of x, and the derivative of cosine of x is sine of x, or rather negative sine of x. And so let's do some problems. Does anyone have a favorite number between 29 and 40? $37. Got it. Between what? Between 29 and 40. And so number 37 is y equals 3x squared times secant x. And so if they want us to find what is y prime of x, then we can see here that we have a constant, but then we also have x squared times secant of x. And so this is going to be one function of x times another function of x, so we use the product rule. And so this is going to be 3 times the product rule of these two, so we'll have the derivative of the first, which the derivative of x squared is 2x, times the second, and so secant of x, and then plus the derivative of the second times the first. Well, we've already got secant of x, and so let's figure out what that is. And so we know that secant of x is equal to 1 over cosine of x. And so we could either derive this technically like using the quotient rule, but I would probably derive this using the chain rule in this instance. And so one way we can think about this is that this would be cosine of x to the power of -1. And so for this, we can think of it like our inside function is cosine of x, and our outside function is this to the power of -1. And so the derivative of this with the outside function is we use the power rule, so we bring down the -1, and then we subtract 1 from the power. So this will be -1 times cosine of x to the power of -2. And then it's times the derivative of the inside. And so times the derivative of cosine, which is negative sine of x. Here, perhaps I should write again what the chain rule is. And so if we have the derivative of f of g of x, so if we have the derivative of all of this, this will be equal to the derivative of f of g of x times the derivative of g of x. And so it's like the derivative of the outside function still composed with the inside function times the derivative of the inside function. So in this case, it's like we're just deriving this as if the cosine of x was just like a singular variable. And so we just apply the power rule to the outside function, and then we multiply by the derivative of the inside function. And so doing that gets us that the derivative of secant of x, or I suppose I should write that here, shouldn't I? The derivative of secant of x is going to be, if we combine these negatives, we'll just get a positive. And so this is going to be sine of x over cosine squared of x, which I can simplify to be sine of x over cosine of x times 1 over cosine of x, which is going to be tangent of x times secant of x. And that's right, the derivative of secant of x has another secant x in it. Isn't that lovely? So yeah, then back to this question over here. So then we have the derivative of the second, and so that's going to be tan x secant x, then times the first. And so all of this times x squared. And so there we go. I guess if I rewrite this a little bit, I will factor out an x and a secant. And so this will be 3x secant of x times 2 plus x tangent of x. And there's our answer. Any other questions that look fun? We could do 40. 40 looks fun. 3x sine of x times x squared cosine of x. If I grab that. Unless anyone had any other favorite numbers between 27 or 40 or whatever it was that I said. 29 and 40. Or you could just say that 40 is your favorite number. Jeff, may I ask how many favorite numbers that you have between 29 and 40? And why are they your favorite? I have an infinite number of favorite numbers. Okay, well, how about favorite integers? Pi times 10? That's a good one. That is a good one. Okay, so g prime of x here. This is going to be the... So I'll write it like this. So we can say that the derivative of all of this is going to be the same thing as like the derivative of this portion plus the derivative of this portion. And so that's going to be 3 sine of x all prime plus x squared cosine of x all prime. And then if we break this up with the product rule, then this will be 3 of x prime times sine of x plus sine of x prime times 3 of x. And then plus the same thing done kind of over here. And so this will be x squared prime times cosine of x plus cosine of x prime times x squared. And so now Well, 40 minus 27 plus 1 equals 14, so 13 favorite. Wait, then does that mean that that one of them's not your favorite? Car on Crack. Thank you for the follow. Welcome in. And so the derivative of 3x, that's just 3. And then so times sine of x. I don't want to be numerist on your stream. Understandable. I appreciate your conscientiousness. The derivative of sine of x is cosine of x times 3x is going to be 3x cosine of x. But I think we all know what number I'm talking about. You're right. All of us know. I especially know. 2x cosine of x. And then the derivative of cosine of x is negative sine x. And so then this will be minus x squared sine x. Can I clean this up? I will factor out the sines and cosines and group those terms up. And so then this will be 3 minus x squared of sine of x. And then plus... 3x plus 2x is just going to be 5x cosine of x. I know a lot about cars, and I know my way around engines, but this hurts my brain. See, I have an immense appreciation for, like, things in cars. Like, I haven't worked on cars, but in principle, I can tell you it's like, oh yeah, I like the... oil pressure and the cams and the lifters and all that stuff. And I probably could work on a car if I needed to. But like, I'm just like, if you point at a car on the road and be like, what car is that? I would just be like, I don't know, a truck? A sedan? I have like no appreciation for brands, but I have appreciation for the mechanics. Well, Car on Crack, if you go back about 1, 2, 3, 4, 5 weeks, or maybe even before then, I don't remember. I think this was our first session. And on my YouTube channel, there's also a playlist. Then you could watch like 16 hours worth of math stream and get all caught up. You'll be a calculus aficionado in just 16 hours. Or not. Or you can just chill out. How the heck can you recognize a sedan on sight? Isn't the sedan just like a small-ish car with like 4 doors? Okay. Let's take a look at a couple of these questions down here. I see when I'm like, this is a car. That's me too, for the most part. I often forget what kind of car I drive. And I have to like look it up. Like what the exact like model of it is. All right, any favorite numbers between 53 and 64? I am taking more applications for favorite numbers. 63. Any other takers? Well, surely it's not just that it's a car with 4 doors. Because can't, like, a truck have 4 doors, too? But then I guess, like, is a truck and not a car? What about a minivan with 4 doors? You gotta be more pedantic in your taxonomical definition of a car. If you just say a sedan is a car, a biologist will stomp in here and give you a 48-hour lecture on morphology. Is a pizza a sandwich? I don't think it's a sandwich. I'd say a calzone is a lot closer to a sandwich. Or is a calzone a ravioli? What's an Uncrustable? Anyways. 63 and 64. I'll just grab both of these. What about open face sandwiches? See, I don't know that those are sandwiches. Like, if I eat, like, avocado toast, then I feel like that's not a sandwich. It's toast. Yeah, like, what about, like, stromboli? Like, why is it that it has to be, like, ravioli? Is stromboli also Italian? I don't know. What's another thing that's like ravioli, but not Italian? Dumpling. Why is it that everything has to be ravioli? Why can't things be dumplings? Okay. 63. And so f prime of x. Pierogi. But is pierogi also Italian? It kind of sounds like an Italian word. No. Well, it says Europe and Asia. That's not very helpful. Polish. They're Polish. Okay, so looking at this one, and so we have one function divided by another function. And so we're going to have to use the quotient rule here. And so if we apply the quotient rule, then we'll have the derivative of the top times the bottom. So times the square root of x squared plus 1 minus the derivative of the bottom times the top all over the bottom squared. And so since this is the square root of x squared plus 1, I'm just going to write x squared plus 1. And so the squared and the square root annihilate each other. And so let's go through here now and figure out these derivatives here. And so the derivative of 3x is just 3. So we have 3 square roots of x squared plus 1. And then the derivative of the square root of x squared plus 1. That's a tiny bit more complicated, because if we look at it, we have the square root of x squared plus 1. So we have an outside function, which is our square root function, and then we have our inside function, which is our x squared plus 1. And so if I write this maybe a little more suggestively, this is x squared plus 1 all to the power of 1/2. And we're taking the derivative of that. And so if we take the derivative of the outside function, we'll be left with 1/2 times x squared plus 1 to the power of negative 1/2. And then times the derivative of the inside. And so the derivative of x squared plus 1 is going to be 2x. And so this is going to be, if I simplify this a little bit, this x squared plus 1 to the power of negative 1/2, I can write that as 1 over 2 times the square root of x squared plus 1. And then times 2x, so the 2 on top and bottom cancel each other out. And we get x over the square root of x squared plus 1. And so that's the derivative of this here. And so that'll be minus that x over square root of x squared plus 1. And then times 3x. All over x squared plus 1. I don't particularly feel like simplifying this very much. Could we? Could we easily? Okay, there's a little bit we could do. If we take this term over here on this side right here and multiply this term right here by the square root of x squared plus 1 over the square root of x squared plus 1, we can get this to become x squared plus 1 and also get a common denominator, which we can then immediately move that common denominator into the actual denominator. And so this would be 3x squared plus 3 minus 3x squared all over x plus 1 times the square root of x squared plus 1. And now these 3x squareds cancel each other out quite nicely. And so this is just 3 over x squared plus 1 times the square root of x squared plus 1. Yay! I can do math. Yep, that looks good. Oh yeah, that was 63. Now 64. And so we have h prime of x is going to be equal to, what was it? X plus 5 over x squared plus 3. All to the power of 2. And then we're taking the derivative of all of that. And so here it's a little more, I feel like at least it's a little clear to see that we have our inside function here, which is our x plus 5 over x squared plus 3. And then our outside function is just that, like, all to the power of 2. And so in this case, we'll be applying the chain rule first. And so we'll take the derivative of the outside function, so we'll bring down that 2. And then we still have our inside is the same. And so over x squared plus 3. And then we subtract 1 from that exponent, so 2 becomes 1, and anything to the power of 1 is just itself, so I'll just leave that as is. And then it's going to be times the derivative of the inside function. And so times this derivative of the x squared plus 3. And so then now looking at this, we'll have to evaluate this derivative right here, ouch, by the quotient rule. And so that's going to be 2 times x plus 5 over x squared plus 3 times this evaluated by the quotient rule. And so that'll be the derivative of the top, which is just 1, times the bottom, x squared plus 3, minus the derivative of the bottom, that's going to be 2x, times the top, x plus 5, all over x squared plus 3, all squared. And so let's see how this simplifies. So if I multiply these together, sort of. How do I want to do this? I'm going to multiply the x squared plus 3 into here to make this x squared plus 3 cubed on bottom. And so this is going to be 2 times x plus 5 all times x squared plus 3 minus 2x squared minus 10 all over x squared plus 3 to the power of 3. And then x squared minus 2x squared is going to be negative x squared. 3 minus 10 is going to be negative 7. And so then if I go ahead and factor that negative out, then I will be somewhat satisfied writing this as negative 2 times x plus 5 times x squared plus 7 all over x squared plus 3 all cubed. Okay. Ta-da! What do mathematicians usually say now? QED? What is that? Quod erat demonstrandum? Or whatever? Okay. Well, I'm happy with that. 3-hour stream. Does anybody have any questions? Anything else we should look at for like 15 minutes or so? Jeff, I'm sure you've got a question. Whether it's related or not to what we're doing. What the heck? Smile? What, do you feel called out? I'm actually using you as background noise as I do something else. That's fine too. Well, then I guess that's it. I guess we're done. No more stream. Should we look at rating someone? Well, wait. If you insist. Do you know Ruby? I know of Ruby. I know Ruby is like the same programming language that like Discord bots are programmed in. But no, I don't. I don't know Ruby. Do you know any command line programs that work with Voronoi diagrams or KD trees? No. I'm afraid I'm useless to you. For now. Let's see, what is this? There's someone streaming. There's someone streaming in the math category right now. That's like their stream title is Khan Academy Speedrun. And their stream audio hurts my ears. but should I raid them? Probably not. Let's see, who should I raid? Who's live right now? Flo's playing Mass Effect. Waffles is doing art. Astral's playing Satisfactory. Let's raid the Astral Hammer. See what they've been up to on their Satisfactory playthrough. See how things are going. I haven't raided them in a little bit, so that'll be nice. Okay, well, thank you for everyone who's joined us this evening. If you're gonna stick around for the raid, go say hi. I should have hit this button. Say hi, be nice. If you like math, you'll probably like Satisfactory. It's like a factory building game that's all about kind of like managing inputs and outputs and resources. It's great. Astral's lovely. Go say hi. Have a wonderful evening. I love you all.